So first of all, good morning, afternoon, or evening, everyone, depending on where in the world you're joining us from. I'm Jarka Glassey. I'm the Vice President Executive of the European Federation of Chemical Engineering, and I'm currently in my second term as the Vice President. I graduated as a biochemical engineer from the Slovak Technical University in Bratislava in Slovakia. And until recently, I worked as a professor in Newcastle University in the UK, actually using modeling approaches to process and bioprocess development and optimization. Thus, I'm very happy to be involved in the introduction of this webinar on solving polymer reaction engineering challenges with modeling approaches. I'm really looking forward to participating in it, at least for a little while. Apologies, I've got a clash today. So first of all, let me say something about the Spotlight Talk series. This is now our 6th year of the Spotlight Talk initiative, which started in 2020 to help us keep together the community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlights into a regular feature of the EFCE program. And we have now one Spotlight series in odd years, like 2025, and 2 in even years. This spring, 11 of our working parties and sections are delivering over 2 weeks webinars with talks on specific topics by leading industrial and academic experts. This series also enables attendees to sample matters in new areas, encouraging cross-fertilization of interests, and the complete program is available on EFCE website. You still have a chance to join a few of our Spotlight series. If you've missed them, there will be recordings available on our YouTube channel. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 chemical engineers in Europe. EFCE's working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE's activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. I would like to encourage you, if you're not already involved with some of our working parties and sections, to consider joining. The section membership is open to colleagues working in the area as an individual member, although for working party membership, delegates are either nominated by their national member society or elected by the working party. If you're interested in joining, do reach out to us through our website where you'll find more information, or through your national member society. Before concluding, I would like to thank all of the people involved in organizing the working party activities, sections, and in EFC in general for this initiative to happen and to be successful. In particular, as always, many thanks to EFCE's Martin Pu in Toulouse, who did most of the conceptual setting up and practical activities. Thank you so much, Martin. I'm pleased to inform you that the EFCE board has decided to award Martine the prestigious Dieter Behrens Medal for her contribution to chemical engineering that will be delivered at the ECAP conference in Lisbon in September. This is very well deserved. So thanks, Martine, and congratulations for this award. I thank you all for your attention and wish all the speakers and the attendees a fruitful and successful webinar. And now I would like to give back the word to Kristina Zentel, Secretary of Working Party on Polymer Reaction Engineering, to start the webinar and to run it. Good luck.
Yeah, thank you very much for starting up our webinar today. So let me shortly introduce myself. My name is Kristina Zentel. I'm currently a junior research group leader at the Technical University of Darmstadt, situated in Germany. And there I'm working in chemical engineering, more specifically polymers. So this is why I'm involved with the working party Polymer Reaction Engineering. So actually, I was happy enough to get into contact with the Working Party already quite early during my PhD, because the Working Party organizes an annual PhD student workshop, which I think is a very nice way of connecting already young scientists in our field, and which is one of the very nice EFCE events that we have, and that just bring the community together. So what are we doing in the polymer reaction engineering area for those who are joining maybe not from the field? So we are applying chemical engineering to polymers. So the speciality, I would say, of polymers is that they are distributed species. So they differ with respect to their chain length and also other properties like monomer distributions. And this is not just a challenge, but this is also a nice way that can be used to tune the process. And this kind of leads me already to the topic of today's Spotlight talk, where we will be looking into modeling approaches that can aid in polymer reaction engineering. We have often highly complex systems, so models can help in understanding on the one hand side what is happening, but then also use that gained knowledge to optimize existing processes, to design new polymers or new processes. And that is, of course, also interesting and important in the context of sustainability, if we are looking at polymer degradation, depolymerization processes. So I think with this, I think we can start the official part of the Spotlight Talk series. We will have a total number of 4 presentations, 2 coming from industry, 2 coming from academia, so we'll have a quite nice overview. Every presentation will be roughly 25 minutes long, and then we will have some minutes for questions. For the audience, you can type your questions into the Q&A tab that is available in the Zoom for you, and then I will read out the respective questions to the speaker, and then we can have the discussion this way. And at the end, the Spotlight talks will be rounded up by a panel discussion. So if we have open questions from the Q&A session, they will move in there. And then, of course, also more general questions can be addressed here by the audience. So I think one very interesting topic will be looking at classical modeling approaches, but also machine learning and artificial intelligence aspects. So with this, I'd like to introduce the first speaker of today's session. This is Nick Ballard. Nick Ballard is Basque Research Associate Professor at POLYMAT, which is situated in the Basque country in Spain. And Nick is very well known for his work in modeling, especially in emulsion polymerization processes. And just last week during the PhD student workshop, one of your students gave already a very interesting presentation about his work. And now I'm looking forward very much to your broad overview on machine learning techniques in the world of polymer reaction engineering. So, Nick, the screen is yours. It looks perfect already.
Okay, good. The practice session worked. Let me try and move this off the side. So, okay. So I can't see your face. So if there's something wrong, Kristina, then you have to let me know. Okay.
Everything is perfect.
Okay. So far, so good. Okay. So thanks, Kristina, and thanks to the EFCE as well for putting on these series of talks. I've watched some of the other sessions online on YouTube, so I found very interesting, and hopefully today I'll be able to maintain the same standard. So what I'm going to try and do today is give a bit of an overview of where, as a group, we're using machine learning models in the world of polymer reaction engineering, and specifically trying to address some of the problems that we've encountered in the past with first principles models and how we can overcome those with machine learning. Okay, so let me start then with a first slide, which I think for this audience is a little bit patronizing, but just allow me to go through it slowly because I think it really makes the main point that I'm trying to get towards. So when we look at the first principles modeling of a typical process, Let me see if I can. Okay. What we generally have is some kind of process parameters. Okay, so we can have some input conditions here, monomer concentration, initiator concentration, temperature, or whatever. And then what we're going to look towards is a model which understands our process and outputs something that we want to know. So this could be the conversion, it could be the molecular weight distribution over time, or whatever it is that we're interested in. And in order to construct this model in the middle here, what we're going to do, oof, I've been too ambitious. There we go. Okay, so what we're going to try and do is first get an understanding of the chemistry. Okay, so we have, in this case, free radical polymerization. We know that it takes place with initiation, propagation, termination. We put together this little reaction scheme. And then on the basis of the reaction scheme, we're going to construct a mathematical version of this reaction scheme. So in this case, we put together some ordinary differential equations. And then the model is simply solving this set of equations. Okay. So the beauty of this way of modeling is really that you input everything that you know as a chemist or as a chemical engineer, everything you know about the system, and you end up with a model which is highly constrained to that underlying chemistry or physics. Okay, so you have a model which is highly constrained. It only has a few parameters. In the ideal case, you say maybe one or two adjustable parameters, which you can then fit to the data. And since you only have a couple of parameters, you only need a small amount of data. Okay? So the problem with that really is that the model that you have is only as good as your chemistry or physics knowledge. Okay, so if you omit something in the reaction scheme, which is taking place in reality, the model is never going to be able to compensate for that. And so that brings me on to the alternative way of modeling, in which the framework is pretty much the same. Let me see if I can get rid of this green line, which I drew there by accident. We didn't practice this. Okay, there we go. So in the machine learning context, you have a model which is basically the same. Okay, so you start off with this initial framework, which is the same as we already saw before. Okay, but the model is constructed in a completely different way. Okay, so rather than inputting all of our chemistry or our physics knowledge, here we have a complete black box model. In this case, it's a neural network. And the neural network is put together with lots of different parameters. I'm not going to go into the details of how this is computed mathematically, but for the sake of this talk, all we need to know is that each one of these little black lines corresponds to a parameter. Okay, so even in a very simple model like this, we might have hundreds or thousands of parameters. And since you have hundreds or thousands of parameters, you need to have sufficient data to justify that. So this comes to the benefit and the drawback of this model is that, unlike the first principles one, which is constrained to the chemistry or physics that we have, the neural network has no constraints. Okay? It's only constrained to the data. So we have then these two contrasting way of thinking. So it's the model that you're putting together is trying to do the same thing, but the way in which it goes about is completely different. Okay, so in the machine learning world, the idea is more data. With more data, you can have more parameters. With more parameters, you have a more flexible model, and you can fit anything in this context. Okay, the first principles model, the thing that most of us would have learned during our studies, is to do the complete opposite of this. Okay, so rather than trying to go for as many parameters as you can, this is best embodied by this quote from von Neumann, which says, okay, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. Okay, so this is the way in which we're traditionally taught, which is to say, make sure that the number of adjustable parameters is really as limited as possible, okay, because that gives you a chance to test how well you can really explain. And so just to give a little proof of this, these guys in the American Journal of Physics really put together this a 5-parameter equation that can make this elephant wiggle his little trunk there. Okay, so the two approaches to the problem are very different, and they have very different benefits and drawbacks. So in the case of the first principles models, the biggest benefit is that once you put this model together, it can really be extrapolated. Okay, you've put your chemistry knowledge in there and your physics knowledge in there, and that knowledge can always be extrapolated to other conditions reasonably. And because you're using relatively small a number of adjustable parameters, you can use these with small data sets. And in contrast, the machine learning approach, okay, doesn't have these benefits, but it has the benefits of being flexible. Okay, so it's not constrained to what we know about chemistry or physics. It can adjust depending on what it sees in the data. So when we started working on this problem, what we tried to do is to look at how we can take advantage of both of these strengths, okay, the strengths from the two different types of modeling, whilst avoiding the weaknesses. Okay, so how are we going to do this? First, in order to understand what we're going to try and do is look at how a neural network learns and how we can adjust that to take into account some of the physics or chemistry that we know. So this is a simple neural network, okay? The neural network here is being trained to fit these 4 data points here, which are in blue. Okay, so it's a neural network which has 1 input and 1 output. And the objective of this neural network is to minimize the difference between the output of the network and the blue points. Okay, so it has 4 points here, and you can see the neural network draws a line perfectly through it. Okay, so this objective function, which is trying to optimize, in this case, is perfect. Okay, it's trying to minimize this function, and in this case, it's perfect. The issue comes in that the same setup could quite easily have achieved a neural network which follows this pattern. Okay, so it's a completely different output than the eventual set of parameters that this network has fallen upon. And you can see that in this second case, both the interpolation, so between these points, is very far away from the 2 distribution, and the extrapolation, so that's looking away from where the data that you know is also very bad. Okay, so it can fit the points well, but it has no way of really interpolating, and definitely extrapolation becomes very tricky. Okay, so the alternative, which is this first principles way of thinking, is to look at this set of data and to try and understand the distribution from which this data is drawn from. So in this case, we might say, okay, for whatever reason, I believe that this process is a 4th order polynomial. Okay, and I believe that the parameters are these ones here. And in doing so, we can then put together a model which doesn't fit the data very well. Okay, so in terms of this objective function, is not minimizing this particularly well, but it fits the trends reasonably okay and is close to the true distribution. Okay, so the question is trying to combine these 2 things. So a neural network only fits the data. Our way of thinking traditionally as scientists is to try and fit trends. So it's to try and find a way to combine these 2 approaches. And the way that we've tried to do that is by simply adjusting the objective function that the neural network is trying to minimize. Okay, so we have this first component, which is always present in a neural network. This first component says the output of the network should fit the data perfectly. Okay, this is this part on the left here. And we add to this objective function a second component, which says that the trends of the network, okay, so in this case, the slope of the line at any given point, should match what we think exists in the theory. Okay? So when we combine these 2 approaches, we end up with a model which both fits the data, but also takes into account the underlying knowledge that we have about the process and can therefore be reasonably used to extrapolate. So then going from a simple line to some polymer chemistry, this is a little example that we've put together here, which is a solution polymerization of methyl methacrylate. Okay, so what we have is a series of 8 reactions in which the process conditions are different. Reaction temperature, monomer, initiator concentrations vary throughout these set of reactions. And we're going to use those. We measure the output in terms of conversion and molecular weight distribution. And this is going to serve as our data-driven component. Okay, so this is the thing where the neural network is trying to fit this set of data. But at the same time, we're going to constrain the neural network so that it also has some understanding of the underlying chemistry that we have in place. Okay, so we put together a first principles model, and on the basis of this first principles model, we can then extract certain information about trends. So for example, we can say when we increase temperature, normally we would expect a conversion to increase and we would expect molecular weight to go down. And the same thing with initiator concentration. When we increase initiator concentration, we expect conversion to go up and we expect molecular weights to go down. When we increase monomer concentration, we expect molecular weights to go up. Okay, so all of these kind of trends that we understand from the underlying chemistry, we can then incorporate in this second term here. Okay? So this second term says the neural network doesn't just have to fit the data, it also has to fit the underlying trends that we know should be occurring based on the chemistry that's in place. Right then, so what we did, we take this neural network. The neural network has as input monomer concentration, initiator concentration, time, and temperature. Okay, so these are the process variables that we know are going to affect the outputs. And then we're going to use these process variables to try and predict conversion and the moments of the molecular weight distribution. Okay? So what we do is we take 7 of the reactions and we use them to train this network. And then we test the model on the 8th reaction, so the reaction that it's never seen before. And when we do that, what we can see is quite a nice result. So looking first at the kinetic model fits the conversion pretty well, but in terms of molecular weight, it's a massive overestimation. Okay, so the kinetic model is not perfect. The neural network has never seen this data before. It's had to extrapolate from some other set of reaction conditions, and you can see that both in terms of conversion and the molecular weight, what is outputting is not very good at all. Okay, so this conventional neural network, purely data-driven approach is no use in this case. When we combine the two things, so this is what we have this, what we're calling polymer chemistry informed neural network. So it's the thing which has the data, but is also constrained to fit the trends that we expect from the chemistry. You can see that both the conversion and the molecular weights are both fit quite well. Okay. We can go one step further, which is since we're outputting the moments of this molecular weight distribution, we can use them to reconstruct the full molecular weight distribution. And when we do that, we can see again that the data is closest to this polymer chemistry informed neural network. The kinetic model is an overestimate and the conventional neural network is getting the system completely wrong. Okay, so to sum up this part, basically what we have is a system where we take an imperfect model. So it's a model where we have some understanding of the chemistry, but perhaps the parameters that we know are not 100% correct, or perhaps we've missed something in the chemistry. So we take this imperfect model, we combine it with a limited data set, and we can construct this polymer chemistry informed neural network, which offers better predictions than either a data-driven or purely theory-driven approach. Okay, so then moving on from there, one of the other main approaches that we've been trying to use in this machine learning story is to really try and take advantage of the much faster inference time of these models. Okay, so typically when I put together a first principles model, I'm happy if it runs in a minute. Okay, if it runs in 10 minutes, it's okay, but occasionally it's the case where it might take an hour or even a day to run these first principles models. Polymer chemistry systems are very complex. They involve big distributions, can take some time to solve the problem. In the case of machine learning, a neural network, one single pass through, takes place in a fraction of a second. Okay? So in this second part of the talk, what I'm going to try and focus on is where we can use first principles models, where we can leverage those to generate a machine learning model, which can offer some advantages, particularly in terms of inference time. And one of the problems that we've been using this approach to try and address is in control problems. So particularly for online settings where you need a response immediately, and with the first principles models, it's simply not possible. So let me give a little overview of the typical setup that we have. So this is a problem that we've encountered over the course of a number of years. We take a measurement from the reactor, and then what we want to do is we want to use a model to say, okay, what's the control action that I should take in order to optimize my final product? Okay, so I'm at a certain point in the reaction. How should I change the temperature or the monomer feed rate or the CTA concentration right now in this moment in order that the product that I get at the end is going to be the optimal one. Okay. So it's a problem because, like I said, first principles models can take a minute, 10 minutes to solve. And when you're doing this kind of optimization process, when you're trying to optimize which actions you should take, it involves running the models multiple times. Okay. So since the models are computationally expensive, this can take a much longer than the reaction itself. Okay. So you end up solving an optimization problem, which takes a few days to solve. But by that time, the reaction is already finished. So there's two basic approaches to this. The first one is to accelerate the model. Okay, so if you have a model which takes place, which can be run in a fraction of a second instead of an hour, then this will contribute to solving this problem. And the second one is to accelerate the optimization. Okay, so if you can make this decision faster, then it allows you to really do this in real time. So the first option of accelerating the model, I'm not going to go into too much detail here. I just have this one slide, mainly because this work from Sabine Baumann and co-workers really has dealt with this problem quite nicely already. So they've got a bunch of papers on this topic. So the idea here is basically you take a first principles model, okay, which runs and gives you accurate results, but is slow, and you use that model to train a machine learning model which outputs the same type of data, but in a much faster way. Okay, so we have our process parameters here. They run through the simulation, and we get an output. And the idea is that instead of taking this computationally expensive route here through the red arrows, we generate a bit of training data. We use that to train the machine learning model. And once we have a model which approximates the original simulation, then we can bypass the computationally expensive route using this black arrow here. Okay, so this is the way of accelerating the model. But like I say, I think is best if you're interested in this approach to look at this work from Sabine Baumann. Okay, then. So the second alternative that we have is to accelerate the optimization. Right? And what do I mean by this? Effectively, what we have in our system is we take some sample from the reactor, some information from the reactor, and we want to use that information to output what the optimal control action is. So in the normal case, like I said, this involves solving a relatively complex optimization problem using a first principles model, which is very slow. Okay, so in general, it's a very slow process. So what if we can avoid this by putting in a neural network here, okay, which is trained so that it takes information from the reactor and it outputs the optimal control actions for the problem that we're trying to solve. Okay, so the problem then converts into one in which we need to have a neural network that is capable of doing this. Okay, so the training process for this neural network becomes the challenging. And the way that we're going to train this is by using the first principles models that we have. Okay, so let me give you a little example here. This is an example from the literature where they try and teach a robot how to walk. Okay, so teaching the robot how to walk basically involves this robot has information about the current position of its limbs, and it needs to then make a decision about which actions to take. Okay, so if it's trying to learn how to walk, which is in this case, okay, it needs to know that you can't move both legs at the same time. First, the left leg needs to go, and then the right leg needs to go. So the process here becomes one in which the system is constantly interacting with the environment. Okay, so it's constantly receiving information about the position of its limbs, and it constantly makes decisions about what to do next. And when it takes a decision which it sees is good, so in this case, for example, it's trying to learn how to score a goal in football. When it makes an action which results in a goal being scored, it learns. The parameters in the model are adjusted so that in future, that same action is promoted. So in that way, the positive actions that are taken are reinforced. Okay, so it learns to repeat those actions when it's in a similar state. And the negative reactions, so those negative actions which result in it falling down or something like that, are then prevented in future. Okay, so it's a process of constant iteration where the model is interacting with the environment. In this case, it's this simulation of the robot, and over time is learning which are the actions that I need to take in order to optimize my end goal, which in this case is learning how to play football. Okay, so we're going to set up the same thing in our polymerization system. So what we have is an emulsion polymerization of butyl acrylate. Okay, so this is what's going on in the reactor here. And at certain times, the system is going to receive information about the state. So the state of the reactor in this case, in terms of conversion, the amount of monomer fed, the molecular weight distribution, which we approximate by a method which I'm not going to go into detail here. And it then has to learn which actions to take in terms of the monomer feed rate, initiator feed rate, and reactor temperature. And it's going to learn those actions, which is the optimum action to take, on the basis of matching the final target molecular weight distribution, which is this one here, which we obtained from some reference process. And it's going to try and do so whilst minimizing the reaction time and ensuring that the reactor is in safe conditions. So in this case, this is simply avoiding very high levels of monomer in the reaction. Okay. So like I said, we have this process of constant interaction with our simulated environment, so our simulation from the first principles model. And at the beginning, the system doesn't know which actions to take, so it's making very bad decisions. For example, it's deciding to never feed in the monomer into the reactor, and then you never have any molecular weight distribution. Or it's feeding all of the monomer in at the same time. Concentration of monomer in the reactor goes so high that it becomes dangerous. Okay, so towards the middle, it starts to learn how to put something together, how to put a series of temperature and monomer feed rates into the system so that the molecular weight distribution that we target is approached. And by the end of the training, okay, so after a large number of simulated reactions, is really learn an optimal control strategy, which both gets the molecular weight distribution that we want, but also does it in optimum time. Okay, so the original molecular weight distribution for this process was obtained over the course of 4 or 5 hours or so. And in this optimal control process, the system has learned autonomously to do it 50% faster than that. Okay, so that's all I have to say. So what I've tried to do is give a kind of overview of where we can use machine learning, leveraging the first principles models that we have. Okay, so hopefully I've shown you that we can use these to make good predictive models, which are not only constrained by our underlying chemistry, but also have a data-driven component. We can use them to accelerate computation. Okay, so we can make machine learning models that are very close to reproducing the first principles models, but order of magnitude faster in time. And we can also use them to solve very challenging control problems using this reinforcement learning approach that I've discussed at the end there. Okay, and so with that, I'd just like to thank the people that paid the money for these projects. And if there's any questions from the audience, I'm happy to try and answer some of those.
Thank you very much for this very clear and nice, understandably and visible presentation, Nick. So the floor is open for discussions. So far, I cannot see any questions from the audience. So if you want, you can type in any questions to Nick now. Maybe I can start with the first question. So the nice example that you showed in the end regarding optimizing the feed strategy. I was wondering, were you also using a polymer-informed neural network for this? Did you also train it with the data from a physics-informed model first?
No, in this case, we're just using the output from the simulation. So it's one of the, maybe if I can go back on this. So it's one of the things that we're looking at trying to improve now. For example, if you look at the x-axis here, this says that we need 4,000 reactions 4,000 simulated reactions in order to reach the optimum control strategy. Okay, so 4,000 simulated reactions in this particular case, really, it takes quite a long time to learn the optimal solution. It's a long period of time. Once it's got there, is rapid. You can be implemented fast, but it takes a long time to get there. So one of the things that we're looking at is using, for example, machine learning systems in place of our first principles model. So in that way, still there will be 4,000 simulated reactions on the x-axis here, but in terms of time, it will be orders of magnitude improvement. So this training process, I think, takes a few days, but we could probably decrease that to a couple of hours if we implement some of the other ideas that I showed in the talk at the same time.
Yeah, really, really nice. So if you use this trained model now and you give it a different molecular weight distribution, will it again need 4,000 reactions to learn, or will it then be faster?
No, the same. It needs, again, will need to be trained from scratch. So we'll again take a few days to train from scratch. There's another one of the things that we're looking at implementing to make it kind of universal. So you can have the target in the initial information, so that it knows not just to fit the thing that he's trying to get towards, but can be more general. So it's something that we're also working on, but at the moment in this particular case would need retraining of the model from scratch.
Thank you very much. So in the meantime, we have two questions from the audience. The first one is from Timo Melchin, and the question is, can the reinforcement learning model for an optimized control strategy cope with randomly occurring process disturbances, for example, failure of a pump or stirrer? How do you treat this?
Yeah, I have a slide on this, but let me see if I can. Okay. You can see this the slide now. Okay,
Yes.
yeah. So let me go back here. I'm gonna unhide these. Yeah, I didn't deal with these for time, but basically in the form in which I've shown it in this presentation, it wouldn't be able to. Okay, so it learns based on what it's seen in the past, and if it never sees those process disturbances, when it gets exposed to them, it also makes bad decisions. Okay, so in this case, when we've never exposed it to any process disturbances, we simulated in the middle of the reaction here a little bit of inhibition, and when we simulated this inhibition, the system didn't make any change to the control strategy. Okay, so it didn't respond properly. But what we can do is, if during the training process, we occasionally put in some reactions in which there's some kind of process disturbance, then it can really learn to overcome those. So as long as it's been exposed to those kind of experiences before, it will learn a strategy to overcome that. So in this case, now when it's been trained with those disturbances, it's exposed to this same inhibition period. And as soon as it sees that there's some inhibition, it reduces drastically the monomer feed rate until it sees that that disturbance has been overcome. Okay, so in this case, it reduced the monomer feed rate. As soon as it saw that the reaction started to proceed again, then it adjusted the feed strategy to get in the end to something which is similar to the goal that it was trying to achieve.
Okay, thank you very much. Then the next question has maybe already been targeted a bit. Sebastian Fries is asking, how flexible is the reinforced model when the starting conditions of the reaction change?
Yeah, so again, it's something where if it's never seen that during training, then it struggles to adapt to those kind of things. But once it's kind of a good and a bad thing. Once you know which kind of things you want it to be able to learn to overcome, generally it can do that. So in another example, in this case, we expose the system to different initial seed. So the initial seed molecular weight distribution, in this particular case, the initial molecular weight distribution of the polymer, which is in the reactor, influences the final molecular weight distribution that we get. So as long as we train the model with a bit of a variation in the initial molecular weight distribution of the polymer that we put in the reactor, then it will be able to learn to deal with that. But if it's never exposed to it, then it will struggle to overcome that when it's implemented in the real system.
Okay, thank you. Maybe the last question, we can keep it short. Salah Hosseini is asking or saying, thank you for your nice talk. Can we call reinforcement learning as an optimization strategy?
Yeah, I mean, basically, this is what he's doing. Like I said, he's learning the solution to the optimization problem, so that when he's implemented, he doesn't have to perform an optimization. It's already been done, and it just learns the output. So he's the alternative way of doing this is with a kind of classical optimization of model predictive control or something like that. And this basically does the same thing, but does it in such a way that the implementation in real time isn't problematic.
Okay. Thank you very much
Okay.
for answering the questions and your presentation again, Nick. Thank you. So we'll see you later for the panel discussion.
Okay.
Thank you. And then we can move to the next presentation, which will be from industry. So the next speaker of the session is Felix Warnecke. He's from Wacker Chemie AG in Burghausen, Germany. So Felix, yes, please, you can share your screen. And his presentation will be about insights into radical formation and efficiency in emulsion polymerization from a modeling perspective. So Felix is R&D modeling expert. So this is, I think, a big part of his everyday work. And I'm looking forward to your presentation. Let me know if sharing your screen works or if you have any questions.
Can you see my screen?
Perfect, yes. And now it disappeared.
Okay.
Can you try to share it again?
Yes, I will try it again. Okay, and now I switch to presentation mode and hopefully it works.
Yes, wonderful.
Okay.
Perfect.
Very good. Yeah, today I want to talk about a modeling project that had the focus to develop a kinetic model for radical formation and efficiency in emulsion polymerization. And yeah, we already had a nice talk, which kind of brought some context to this first principle models here. I will talk about this first principle models. And I think you're all quite familiar with emulsion polymerization, but nevertheless, a short introduction. In emulsion, we have these different phases. We have our monomer droplets, the aqueous phase, and lattice particles. And there are already in the aqueous phase a lot of sub-processes running. You have initiation, propagation, all this stuff. But today I want to focus on the radical formation itself. And the radical formation by redox couples. Redox couples are state-of-the-art in industry if you want to run efficient emulsion polymerization, because redox couples offer some advantages. For example, you have a close to dosing controlled radical formation, and this gives you a degree of freedom that you can really design your process. If you want to have a certain amount of radicals in different phases, you can really design this with your dosage controlled radical formation. And this can help you to highly improve the space-time yield of your recipes. And another important aspect is that redox couples are very safe because you have no accumulation of your initiator. And if you stop the dosage of your redox system, the polymerization will slow down to zero. And yeah, I will talk about one example with potassium persulfate and ascorbic acid, and our project where we tried to develop a kinetic model for this redox couple and embed it in our polymerization models. But first, I want to talk about the process of model development itself. I think we've already heard a lot about this from Nicolas Ballard. Here, a little different perspective. We all know that reality and chemistry is very complex, so you can never fully grasp all this information. That's one topic that was already addressed. So you know, models will never be perfect. The only thing we can do is we can observe certain processes by sensor technology and analytics, and we can capture a certain part of the reality. And especially for emulsion polymerization, you're already losing a lot of information in this process step because you have all these different phases. And just to give one example, the diffusion process for all the individual components, that's not really accessible by sensor technology. So the next step after you captured some parts of the reality is to define your model. So it's an abstraction process of what you want to do. And this is a very important part because you have to really choose your degree of detail wisely because it has to fit to the question you want to answer and also to your available data. So model complexity and your available data, you have to weight this carefully. Yeah, this is a rough categorization of models. I think we have heard today that there are also other options with artificial intelligence. I want to talk about first principle rigorous kinetic models, which have in general a high predictive capability. But if you want to train these models and have valid kinetic parameters, you need a lot of high quality data, and often you have a long time to develop these models. So if we take a look at a typical model abstraction for emulsion polymerization, you will at least have these sub-processes here. You will always have an aqueous phase and this aqueous phase kinetic reactions going on here. You will also have your polymer kinetics in the particle phase. And these phases are connected by different diffusion processes, for example, for the radicals or oligomers or something like this. And in addition, phase equilibria, which distribute, for example, the monomer over the phases. So in general, emulsion polymerization is a complex process, and you will always have a lot of sub-processes and therefore a highly complex model. Yeah. Today, I want to talk about the radical formation in the aqueous phase. So this was the focus of our project, to have a better prediction for this part here and to successfully embed this in already existing thermodynamic kinetic models we develop. So now coming to our example. The redox system has mainly two parts. The oxidation step, so the persulfate reacts with iron to form radicals. This is very quick, a reaction running very quickly. And to keep this reaction running, the iron has to be regenerated by a reducing agent. A commonly used reducing agent is ascorbic acid. Ascorbic acid is a very complex molecule. You will have a lot of complex intermediate steps. So this is here just for simplification to talk about the modeling. But in general, you will have, if you take a look at the literature, you will have at least two regeneration steps for iron by ascorbic acid. So our first model candidate that we wanted to test was the combination for this oxidation reaction in combination with the regeneration of iron from ascorbic acid, followed by further consecutive steps of our already existing kinetic models. So we have these three reactions here, oxidation 2 times regeneration, and we tried to do some experiments to get access to this kinetic parameters. And in a first step, we started with aqueous experiments. So we tried to reduce complexity from the emulsion system, and we wanted to get access to the composition of this component of the initiator components. So we prepared an aqueous solution of potassium persulfate with iron, and at some point we added the ascorbic acid, and with Raman spectroscopy we could track the consumption of these components, as you can see here in the figure. To get the access to the signals, we had to work with increased concentration levels, so in the range of 1 to 3% weight percent of potassium persulfate in an aqueous solution. In the next step, we did some variations. For example, we did a variation for the iron concentration. And as you can see here in the figure, this is the consumption of the persulfate. The redox system will speed up if you increase the concentration of iron. Another observation is that if you increase temperature at a fixed iron level, the reaction will also strongly speed up. So the question was, can we describe these observations with our three reactions from our first model candidate? And the answer is yes. So we could capture the temperature effect, as you can see here, and we could also predict the reduced amounts of iron. So some straightforward trends. And as this worked quite fine, the next step was we wanted to challenge our model in emulsion polymerization. Therefore, we switched to an emulsion polymerization system with vinyl acetate as monomer, PVOH stabilized, and we developed a recipe with a solid content in the range of 55%. The drawback now is that we have no more direct access to the initiator components because the concentration level of the initiator is simply too low. So instead we can track the monomer conversion in form of the solid content in our case. So we still wanted to stay at our initial model and take a look how it performs. But first, one thing I want to mention is that data quality is extremely important if you want to do kinetic modeling. So in order to get access to the monomer conversion, we had different approaches. One approach is to set up an energy balance and calculate the heat of reaction and convert it in a solid content. So we did this energy balancing for our 2-liter lab reactor. Another way to get access to the monomer conversion is again Raman spectroscopy. So as you can see here, the signal of the vinyl acetate monomer is shown here, and the signal of the vinyl acetate in polymerized form is shown here. In the intermediate range of conversion, we have overlapping peaks. So this is not a perfect situation, but it still is working quite fine. So again, data quality is extremely important if you are doing kinetic modeling. So I recommend you should always validate your experiments and check for the quality prior you start with a modeling project. So what you can see here is the solid content from different sources. In blue, you can see the Raman signal. Green shows the energy balance. And this orange stars is an offline sample where we analyzed the solid content by weighting and drying the samples. So now coming to the experimental results of our variations of the redox system in emulsion. And the first, a little unexpected result is that if you increase the iron concentration in your system, you will see a strong decrease in reactivity. And our interpretation for this that is that iron has a negative impact on the radical efficiency. And if you take a look into literature, you will find the assumption that iron 2 is not only working in the redox system to speed up your redox reaction, but it will also destroy your sulfate radicals. So you have to choose the concentration carefully. And another observation was that if we increase the ratio of ascorbic acid compared to the persulfate, so not the stoichiometric ratio, but go away from this for lower ratios or for higher ratios, we will also see that an increased amount of ascorbic acid has a negative impact on the radical efficiency. So the question is also, why is this happening here? So we did some variations, collected some data, and then we started the first modeling approach. And here you can see this is the stoichiometric ratio for persulfate and ascorbic acid, if at least related to these equations here. And you can see if we adjust the kinetic constant for the radical losses, we can describe the solid content here with the blue line quite fair. But if we change the ratio of persulfate and ascorbic acid, the model strongly fails to predict the solid content. So here we have an under prediction of the solid content with low amounts of ascorbic acid. And for high amounts of ascorbic acid, we have an over prediction of the solid content. So our model fails and we had to revise our assumptions. And if you take a closer look in the literature, you will come to the point that ascorbic acid is more complex, and it seems like the degradation products of the ascorbic acid, for example, the oxalic acid, but it can also be some other component, we don't know that for sure, will also act as an reducing agent, and so we have further reducing potential here if we add 1 mole of ascorbic acid. So our approach was to add another generic reaction to depict this observation here. Another unexpected observation was that we have also tried to do some thermal polymerization with potassium persulfate, and the reaction was running quite okay. And if you are not looking, the start was not that fast, but once the reaction was running, the batch with thermal decomposition of persulfate was running quite fast. And this was in contrast to the literature constant, because we have also tried to simulate this prior with the constant from literature, and with this kinetic constant, there was nearly no solid content formation, because the literature constant says that the decomposition is very slow. So we took a closer look to the thermal decomposition as well. So this is here the kinetic constant from literature for the thermal decomposition. So for low temperatures, it is really very, very slow. You will have to wait for hours to get a conversion of the persulfate. And we tried to validate this kinetic constant and did this with our aqueous experiments and checked that it was okay. We did this experiments at 90 degrees and we could validate the kinetic constant from literature. So in the next step, we tried to validate the persulfate decay in emulsion. And that's not that easy because we do not have the access to the initiator components because of the concentration. So we had to think about another strategy. And what we did was we did pulsing of potassium persulfate, as you can see here in the figure. Here we have 1, 2, 3, 4 pulses where we dosed some amount of potassium persulfate, and then we observed how the solid content reacts. And our assumption was if there's no more radical formation, there will be no polymerization. So that's why you can take the solid content as a reference. And what we see here is that the living time of polymerization is very, very low. So in this case here, for our first pulse of initiator, we only had about 8 or 10 minutes living time, and after that the reaction stopped completely. And this doesn't fit together with the half-life time or the kinetic constant in aqueous solution. And if you take a look into literature, we are not the first ones who have observed this phenomena. For example, at 50 degrees C with vinyl acetate, in literature there's reported that the thermal decomposition is 15 times higher than the constant for aqueous solution without monomer. So this is in good agreement with what we have observed. It is not that easy. You cannot simply take the decomposition constant and put it in your model. So it's more complex. The explanation and the theories, it's even more complex. It's quite hard to really get sure what's happening here. But the theories are, one theory is that the monomers are building like a cage and trapping the sulfide radicals, and therefore avoid the recombination of two sulfide radicals. So one theory or another theory is that there is some transfer to the persulfate. We don't know for sure, but we have seen this observation that the decay is strongly increased in the presence of vinyl acetate. So we had to revise our model again. So our initial model with the 3 reactions was extended with 1 reaction with additional reducing capacity for the ascorbic acid. We also had to add this radical losses by iron. And additionally, we also had to add the accelerated thermal decomposition in the presence of vinyl acetate. And with these new assumptions and the strongly more complicated model, we were able to regress kinetic parameters that can fit different observations for different persulfate to ascorbic acid ratios and also the thermal decomposition. So this is a first step. We could describe a couple of observations. But of course, we are not done here. There's still a lot of things to do. But I hope I could show you that the initiation in emulsion polymerization is a complicated topic. And our opinion is that in literature, it is often not really treated with the appropriate importance because it has a really strong impact on your process. And we think that understanding the initiation is essential for the model development because you will always have also this interaction with all your other kinetic parameters. Okay, so that's it from my part. Thank you.
Okay, thank you very much, Felix, for your very nice and detailed presentation. Again, now questions are possible via the Q&A tab. I will have a look at them. In the meantime, I'm interested in having a first question myself. So I really liked how you put effort into validating your experimental conversion with the different approaches. And you showed the energy balance as well as the Raman results and also the overlapping of the peaks. And I was curious how you dealt with that, because I think the results are in very good agreement with the energy balance model and also the offline analytics that you showed. Maybe you can elaborate a bit on how you work with the peaks.
For the Raman?
Yes, this one exactly.
Yeah. Okay. So we have a lot of spectra here. So we take a spectra every minute, And for every spectra, we are doing this regression of the peaks to fit the raw data signal with a fixed position, more or less, of the middle of each peak. So we did not change the the optimization has only a very low window to shift the middle of the peak. Yeah.
Okay. So you did a deconvolution of the peaks, right? No, you shifted the middle. Okay.
Yes, from some data we know quite well where is the maximum of the peaks.
Okay.
And yeah, this was our reference where the peak should be. So we do not allow the peaks to shift too much, because then you will have some quite strange optimization results. But if they are fixed more or less and can only shift very small numbers, then you will get quite nice results.
Thank you very much. So I think we have a question from Nick. A very interesting approach to a very hard system to try to analyze. Ascorbic acid KPS by itself is also a redox pair. Is there a reason that the reaction between these two can be ignored?
I think I can answer the question with this figure here. If we have no iron in the system, we have a certain reactivity of the components, but it's not really known if it's a reaction between the two that is responsible for this decay here, or if there are still some minor traces of metal ions. But as the reactivity was quite low compared to the cases with iron in the range where we use it, we more or less ignored it and gave it a small amount of metal ions for the, let's say, zero reactivity.
Okay, thank you very much. You have a question?
Yeah, more comment, Felix. If you go back to the spectra you had before, it was you could see that you have a nice curve with conversion, but you have not a direct isospastic point, so that you have some side effects in between there. But what could also be done instead of the fitting procedure is there are some routines for spectrometer software that do a half band integration from finding the individual peak maximum towards the baseline. And if you would take the half band to the higher and the lower wave numbers respective for the individual peaks, it could give also a nice result, because under these circumstances, then the half bands are free from side effects.
Okay, yeah. Thanks for the comment. One thing maybe is important to mention here, with increasing degree of polymerization, both peaks will strongly lose intensity. And what we did here, we were always working with the ratio of the peaks. And we have a fitting parameter here, and we're working with the ratio. If we would not do that, we will not have this good information, because fitting for concentrations in emulsion polymerization is nearly impossible.
Yeah, that's true. And taking the ratios is extremely helpful. The other thing what you have to watch at is that you are still in the linear region of the detector, so that the intensity is not too high. So covering a broad range of conversion, specifically in the infrared or near infrared. Sometimes you run into these problems, but this helps them if you switch to the next overtone. So then, or if you have if you're going too high in concentration, then you're switching to the next overtone, which means that, and the fortunate thing of the overtones is that the spectra the peaks diverge, so they move, they spread more, not the peak basis, but the peak maximum move from each other apart.
Okay.
I was too long working in a department with infrared, near infrared spectroscopy. Sorry for that.
Okay, so I think we do not have any more questions from the audience. So Felix, thank you very much for your very nice presentation and the insights into the radical formation and efficiency.
You're welcome.
Over to the last speaker of today's Spotlight talk, which is Markus Busch. So he's sitting now here with me. He's working in chemical engineering at the Technical University in Darmstadt. And there he is the head of the high pressure polymerization technology labs. So working with alpha olefin polymerization, specializing on LDPE, high pressure polyethylene and copolymers. And he will be presenting about bridging the scales in this area. And so with this, I think we can hand over. Let's share our screen. So now please someone else from the panel can maybe let us know if this is working.
Yeah, looks good.
Perfect. Thank
Welcome, and sorry, but I'm rushing in late. There are other appointments within the university, but I'm happy to join here and to talk about how to transfer the scale from the lab to large-scale application. And to give you an idea what we are talking about, we can look at this picture. So the typical thing in high pressure labs, but also I think in many of your labs, is that the cell size is about 1 milliliter or something like this. So this is a typical high pressure cell you can see. We are running a few mini plants and they have a reactor volume. So here you can see the reactor and the volume is about 100 milliliter. But what you have in industry, and part of you know, is looking a lot larger. And what you see here in the background of this person is just the reactor bay. It is not the full plant. So this is the full mini plant, but this is just the reactor bay. So we are going from 1 milliliter of reaction volume to, in batch mode, to 100 milliliter of volume continuously operated around with throughputs about 1 to 6 kilos per hour. And that is capable of generating samples around 1 kilo or 5 kilo or something like that, here to production rates that are measured in tons. And normally you would say, yeah, just avoid non-idealities and then you're fine. But that you can run into pitfalls. You can see here down in the bottom right, where you have identical reaction conditions, and once in a smaller reactor and once in a larger reactor, still both on lab scale. And you see here that you see significant deviations in the area of high molecular weight, which is due to fouling and the unfortunate surface to volume ratio on lab scale. So that's a point you have to avoid and what you have to be aware with, and you have to deal somehow with this. And what I'm now starting with is not really new thing. You see here 3 publications that are reaching back to the past. And the point is with these publications, but I could have also cited Archie Hamiak or Harmon Ray. So these are the grandfathers of our field, meanwhile, maybe grandfathers. But the basic ideas have been very visionary and they are still holding. So if we are a little bit critical with ourselves, it is we are all working on old ideas and old stuff. I'm personally very related to these because my first job interview on a habilitation position was running like that. Do you know these 3 publications? No? Read it. I would like to discuss it with you in half an hour, and that was Karl-Heinz Reichert. And he brought to me the idea about taking up the idea that on the one hand, polymers are product by process, and on the other hand, the basic idea, the molecules growing do not know about their environment, and if we have laboratory experiments, if you have synthesis conditions, if you have a synthesis strategy, or if you have process conditions here, we have a kinetic model. It should be the same in any case, and we would get reaction rates, so all the parameters for productivity, we would get molecular properties, and they are the detour to applicational properties. And so this is the basic idea. If I have a good kinetic model, that's the core and the heart of all, then I should be capable of modeling in any plant, in any reactor, in any lab reactor, I should be capable of modeling these reactions, and that should work. And in pictures, it is like this. During that time, I'm still talking about the 90s, we moved away from overall kinetics to elementary kinetics, understanding chemistry as a combination of elementary reaction steps. And that came from physical chemistry, the idea, and this is where I did my PhD and my habilitation thesis. And if this is working, it should be capable of generating the molecular weight distribution reaction rates as you are seeing here, and apparently it works quite good, at least on lab scale, and the question is how to move on. During that time, and now I'm coming back, I'm moving to future or to the actual times. The question is which technology you should use. And in the past, you could use, due to computational limitations, you have the method of moments. The scientists in the vision of scientific truths used Monte Carlo techniques, and there are lumping techniques also. So each being focused on how to handle certain limitations. But nowadays, it is most or less all the groups that are working in that field converged somehow to apply a hybrid of kinetic simulation that is good for the process with dealing with ODEs, the Monte Carlo process as a hybrid on top of that, saving a lot of computational efforts with relying on the reaction frequencies from ODE modeling and generating the molecular structure that is again transferred to then other models that deal with rheology and application properties. And the good thing with this is that you have a modular toolbox which you can fit together individually, and if the interfaces are right, so here the interface is the reaction rate, here the interface is the molecular structure. If you put the interfaces right, you can also switch in between these models, and it is getting very versatile. On the other hand, it is directly following the old idea. Reaction kinetics are generating structure, and the structure is generating applicational properties, and that's working pretty well. And some kind of irony before, when groups were discussing which is a more fortunate way to go. Meanwhile, we are all converging to this approach, and this sees that interaction in science and is a good thing, and that we move forward. And that this is not only a dream and a vision talking about, you can see here, you get the molecular weight distribution between experimental data and simulated data. You can get into the Monte Carlo process, generating a structure and deriving from that structure the microstructure and application properties, and you can go into rheology and see what is happening there and what application properties are doing. And if you do so, and Kristina is working quite in detail with that, for example, you can have also validations. So no model is good. Modeling is nice, but it is nothing worse without a proper validation. So otherwise it is just fitting, and for fitting you need a pen and a piece of paper, and that's it, plotting the data points and drawing a line. But if you validate it in an independent set, then, for example, here you take the microstructure, you take the random walker, you evaluate the space a molecule is occupying, you look for the contraction factor, so the relative space to a linear chain that is occupied with respect to molecular weight, and you can see that you have the Monte Carlo process here, you have the experimental data over here, and you have the simulation over here, and you see you can get it to nice agreement. And that's it, basically the very first elementary concept, that if you have a proper model, if you have a proper set of rate coefficients, then you can describe, independent of what you do at different places in different reactors, your application properties or your properties of the polymers, and that's an important thing. So if this is really true, then you should work with, you should look at different reactor technologies. And the fortunate thing, aside of that, we have an additional playground pressure in our system. We have a we have a technology at hand where two major directions of reactor technologies are implemented. So it's a multi-zone autoclave that's going back to the ICI licenses, and it is a multi-zone tubular reactor that is going back to BASF licenses. And at the end of the day, the nice thing with this is that these two reactor technologies, due to their back mixing characteristics, deliver very different products in terms of application properties. Sure. So you have the autoclave reactors are much more for shear strengthening than the tubular product, and those who are working in that field, such as our colleague from SABIC, they know pretty well about that. And the good thing is now that we have a very nice test set to see whether the idea of kinetics is working. And you see the molecular weight distributions are well captured for both reactor technologies parts. And this is a good indication that in the first instance, this idea, one set of kinetic data, two different reactor technologies, and I could talk now about the different reactor sites, and from one of our partners or different of our partners. It's always the same thing. We would expect that everything is working nice. The boundary conditions for this is that we put, or that we blame the right things. So enthalpic things should be blamed to the enthalpic part, back mixing things should be blamed to the back mixing part, and kinetic things should be blamed to the kinetic part. If you have cross correlations or there or misfits in between technologies, then you should watch whether the model is these three things are attributing in a right manner. So that's an essential thing. You could use that for an expansion study, and you see in the first instance this is looking good, and you could be happy. But if you go into rheology, you see there are still some kind of discrepancies where you have to chase after and correct for that and process conditions. But it is a very nice thing to speed up a recipe development and recipe adaptation for reactor expansion projects, and that's working fine. So we could be happy at the end of the day, and we could lean back and see, well, the job is done. I'm going to pension. That's all, and see you at the beach. But the point is, I talked about enthalpic aspects and I talked about backmixing aspects that play a role, but I didn't say anything up to now about that. And so the idea is if this transfer by modeling is working fine, it should be working that we study mixing and enthalpic effects on small scale, and then again transfer the knowledge, because nobody likes to play with a 1 cubic meter or 5 cubic meter high pressure reactor and use that as an experimental toy moving along. You can do that. It's quite expensive, and if it's running bad, then you create quite a bit of mess. But as we are beforehand running these 100 mil reactor, and the idea was, well, for mixing things, we should move with the lab scale into the direction of the industrial operation modes. We expanded that in terms of a 3-zone reactor, and the first thing is, well, do we have the right back mixing characteristics? So what shall we do with the reactor inner parts, and how should the mixer look alike, and can we do that? And again, modeling can help. So on the top end, you see here the experimental tracer experiment with a color tracer of a pulse experiment with the mixing characteristics, and in the bottom, you see the simulation, and you see the simulation matches nicely with the experimental data, and it is a 1-to-1 replicate of the conditions on a high pressure autoclave. The viscosity, which is the demand or the major demanding parameter for the mixing characteristic, has been adapted to the high pressure system, and the geometry is exactly the same. The only thing is we build it from PMMA so that we can look inside. We make a transparent stirrer so that we just see the back mixing characteristics. And by this, we have now, for designing and for quantifying back mixing characteristic, a nice tool. And then we can build a high pressure autoclave like this. We can optimize the stirrer in a way that you see here, that zones are well separated, that back mixing, the radial mixing is working properly. So this is what we all did. And then we characterize that all and see that we have indeed a nicely working 3-zone autoclave, well separated. If you don't put in baffles or baffles in the wrong configuration, it is looking like this. If you're doing it in the right way, it is looking like that. And with this, we are quite happy working with that. And then you can start playing. You can do now similar things. Like in industry, you have a multi-zone autoclave. You can feed initiator or co-monomers at the top, at the side, and whatsoever. You can keep the zone separated. You can play around with that. And what you can see is that indeed products come out different and different in properties, and you can model or use modeling again to understand that, to test if your concepts are right for the back mixing. And the good news with this is then you can do that all with all the degree of freedom on lab scale, with going to the extremes, which you would never do on large and operational scale. But if the models will hold here, it is likely that the models will hold also in large scale. And you can use modeling again to understand how molecules look alike. So if I feed every comonomer on top, it is looking well and nicely distributed. If I feed it at the side and the top, I find a little bit of comonomer in the core chain and more of the comonomer in the side chain. If I feed it all in the side, I have a homopolymer core and side chain with a high content of comonomers. And by the way, the composition, the average composition of these molecules is all the same. So that's how you can access a molecular design of molecules. You can also go to mixing characteristics, so initiator efficiency. So if all is ideal, the initiation process, the mixing process, you would have no initiator efficiency, only the chemical efficiency. But if you have an injection plume, you have primary radical combinations, and this is causing these non-idealities in the initiator consumption curves, this optimum curve, and you can characterize it, you can build up models, you can see whether these models depict in the right manner the control of the molecular weight distribution if you change peroxides, for example, or you can study how peroxide cocktails interfere. This means you can have more productivities, but you can have also interferences, and that's it. Yeah, and if we are, so this is what is, I would say, ongoing concepts where you say we do the transfer, and the next thing is that we go to a more visionary part, and then you have these stories like I have an initial peroxide injection, and I would study what happens here, and do I generate a hot spot in a reactor or not, and what happens with the hot spot, and this is when you drive your reactor to maximum performance. And if you overdo it, things like these happens. So you see here that a typical deflagration of an ethylene mixture under high pressure, and you see it matters where the ignition point is. Is it at the top? Is it at the bottom? It is looking completely different. It is giving completely different decomposition profiles. And at the moment, modeling is here in a state of the art that we can describe the deflagrations, we can identify hotspots, but the models are not interlinked in a manner as I have presented before for this three-step modeling approach. This is something that has to be done, but this is also how the old stuff grew. You have a description here, you have a description there. You look for the right interface, and if you have identified the right interface, you can link each model to each other, and that's fine, and that's future work. And then you have really a digital twin, not only a digital twin in terms of productivity and operation modes, but also in failures, and that's what the future is about. Yeah, this is not all my work, because I'm only the guy who is torturing students with crazy ideas. There are people and there are hands that have to manifest that. These are the hands. This is the group. It is our group. It is Kristina's group. We are sharing visions. We are sharing methodologies in terms of either emulsion or high pressure technology, and the modeling technologies. So this is these are all the hands that are working on that. And you need friends around the world, and part of a few of them are also here in the meeting that feed you with money so that you can pay your bills, but feed you in terms of challenges, in terms of what is next, where to move to. And this is something that is making work very challenging, but also very nice. And you have a lot of good perspectives. And I think with this, I'm at the end, and I'm hopefully more or less in time, and I'm open for questions.
Yes, we're perfectly in time. Thank you very much for this nice and very broad overview of the activities. May I quickly have
Yeah, I think I give back control and see whether we have something.
So far there are no questions in the Q&A tab. So you have showed nicely how well the models fit together, and how nice you can transfer them from lab scale up to industrial scale, also for different reactor types. And of course, this was also a way to go. So looking back at modeling, what were the biggest challenges you would say in getting to this?
It's that's a difficult and easy question. So the frustrations came always then when a model was not fitting. Mm-hmm. And we had, during my habilitation times, we had a postdoc, or also my PhD times, I had a postdoc that was Greg Russell. And he is a pure theoretician, and he taught me coping with it in terms of, it is not a failure if a model is not fitting, but it is a challenge to find new things. Because if a model is not fitting, it is indicating that you did not identify something in the correct manner, and you have to dig deeper and get insights, and then you learn what was wrong, and then you make your model better. I think if you you see that there were some breakpoints. So like the high molecular weight shoulder in the in the molecular weight distribution, which was well captured by Idema, it was well captured by Kiparacides, but they went different ways. So Idema took the terminal double bonds as a sender, Kiparacides took the back mixing. Both, if you have not an additional sensor, is doing its jobs, but if you're leaving your own sphere where you are working, going to a different domain, so a different partner, different reactor technology, that was a problem. And then you learn that you're squeezing things where they do not belong to. And I'm now very happy having the own multi-zone autoclave, because then you can play with these reinitiation scenarios and so on and so on. So beforehand it was, yeah, I'm taking my ideal reactor. Now I take the ideal reactor as a base and focus on the reinitiation. The deflagration issues is, yeah, you can talk about more efficiency, driving the peroxide more to its borders, but then you were confronted with those who are running these large plants and who are responsible for the safety. And the question, can I do this safe? And you have to be always open to these questions to be accepted and keep the contact to reality. And this was the point where we say, okay, yes, if we work on cocktails, if we work on peroxide efficiencies, in parallel, we have to care about hotspots and deflagration. And I think these are the things. And the other things are technological hurdles. So if you look at computational capabilities nowadays and in the past, yeah, with each new generation, you earn something new. So that's, I would say, it's there are plenty challenges, but always it is a start to move to new frontiers.
Thank you very much. So currently there are no open questions also in the Q&A. So thank you, Markus, for the nice presentation again. And with this, I would like to invite all speakers of the sessions to turn on their cameras again and unmute so that we can move on to the panel discussion. So again, now I invite also all participants, put open questions into the tab. They are welcome. If you have a specific question for one of our speakers, please add to whom it should be addressed specifically. Otherwise, I would just give it to all presenters. So Sapriya, I'm not sure if you can hear me. Currently, we cannot see or hear you. If you can see and hear us, would be great if you could join for the panel discussion. Perfect.
There she's coming.
That looks good. Perfect. Okay. So the first question I would like to give to all of you, for some, and I guess it was tackled already a bit in their presentations, but the question would be, what were the main reasons or motivations why you started or still start nowadays modeling in polymer reaction engineering? So what were the specific reasons or motivations that you encountered most? Maybe I can first give it to Nick because you were the first presenter.
Okay, sure. I think that one of the main reasons that we try and use the approach is when you start putting the mathematics, you really test whether or not you understand the system. So quite a lot of the time in chemical systems, it's easy to hypothesize and imagine that you have a good understanding. But when you start to put together a model, it really tests whether or not that's feasible and correct. So I think Felix had the example in his talk where it's a very complex system, and it would be easy to as to be honest, until I saw this talk, I've done previously is to say, okay, I think I understand the system. There is a few different components and they react together in some way. But when you start to try and understand that mathematically, you see that really it is more complex than that. And only by looking into the mathematical details can you really begin to understand. And without that, you're not capable of extrapolating to places where it's really interesting.
Yeah, maybe stepping in there. So when I'm asked sometimes for the students how to or why to do that, I say, well, see, it is good that it is helping you understanding complex behavior. So we, as a mankind, do hard with nonlinear understanding or dealing with nonlinear behavior, and models help doing that. And I would say the strong interference between experiments and models is a good thing. So if you have the opportunity not only to drive models, because at a certain time you spin in circles and you generate ideas where the practitioners would maybe think, oh, this is a little bit weird. On the other hand, the practitioners often have simple hand-waving explanations, which are not completely true, let's put it that way. In the visual observation, they are true, but maybe not in the background, and that's the point. That's from the theoretical point of view. But at the end, to be honest, at least with me, it was a frustration of my PhD father. He was measuring accurate, well, that was Michael Buback, and he was really measuring accurate kinetic array coefficients, and I think a few of you use them still. And then he said, oh, we are doing so much work in the lab, so many efforts, and then there are only a few numbers in the publication, and the simulation guys come and use them and create all these nice scenarios. Why don't we do that? And so that was the starting point, sending me out building the fundament for the modeling part. And that kept me, that intrigued me somehow. But at the end of the day, it was like, okay, we are generating this. And I would understand that as a tribute. We should be grateful for those who generate the data. So that's an extremely valuable thing. And it took a lot of efforts. And when we were on the symposium to honor Harmon Ray, a few of his students said, getting 1 molecular weight was the work of 1 week. Today we put 60 vials in an autosampler, and overnight we have the molecular weight distributions. They had to work for 1 number week, and I think this owes a lot of respect and how accurate they did it.
That's true. So maybe some comment also from, let's say, the industrial side. Felix, do you have to add something?
Yes, I think the main idea was already answered quite well. From industrial side, of course, we want to optimize our processes and our products for sure. And my personal experience now with emulsion polymerization and modeling is that you can learn much faster also for the future generations if you combine modeling with experiments. And yeah, I think that's a big challenge for the future. So many people with a lot of knowledge will retire, and I think modeling can be one way to really capture knowledge and besides all this optimization and deeper understanding of things, I think this can be really valuable.
That's true.
Yeah.
And Sabri, from you, do you also have a comment?
Yeah, I think the pyrolysis modeling effort, at least the attempt we had at it, I was really motivated by the claims of different parties and the observations of different parties on not having a real basis to compare the scalability of different processes for us. Because, as I said, you had very uneven conditions to compare across. And it's really difficult to extrapolate to anything in industrial scale with the basis that is maybe a pilot unit that processes a certain type of feed that you might not see when it has turned into an industrial process. And the only way to make this translation from pilot scale, demo scale units to what it will look like in an industrial unit, what your limits will be. Because you might be presented with, this is a beautiful technology, it's going to deliver you this quality of, I don't know, pyrolysis oil in this case. But you will not be able to build this at a scale because you cannot put in the heat into the reactor that you are proposing. So it's going to have different temperature profiles, and the quality of your product will be completely different for that reason. Or going back, you see people struggling with operation of their reactors. And then if you have a small company who is equipped with a few engineers, really good engineers, but not the overall insight of a trained reaction engineer, they will control the temperature in the melt, and then they are going to have really high temperatures on the wall, which will coke their reactor in no time, and they will have very short batch times and low productivity. So it is really in understanding how we can help
Yeah, I think Timo has put a question to the chat.
Exactly. Yes, we have. Thank you very much. We have another question for the panel. So Timo Melchin is asking, what can we gain for the PAE field, combining accurately determined rate coefficients and in-depth understanding of the chemistry with machine learning approaches like Nick presented?
Yeah,
Mr. Bowers.
I think Nick is the one to answer.
Yeah, I don't know really. I mean, I had the 25 minutes where I tried to answer that question. So maybe I can say why I started to get into machine learning, which was really to try and overcome some of the issues that we have. For example, when I have a model which fits the trends of the data well, I'm happy. But then if you want to produce a polymer which has a certain molecular weight, this model might be no good. So it can predict the trends. It looks like you understand the chemistry. You saw a bit of that in the talk from Professor Busch, I think, where the discrepancy between the model and the experimental rheology was small but apparent. No, the models are clearly capable of extrapolating from molecular structure to rheology. Is understood. But in terms of a quantitative matching, perhaps there's always a little bit of mismatch. So where I feel like the machine learning aspect comes in useful is to respect what we know about the chemistry, respect what we know about the physics, and maybe just apply that little bit of fudge factor, if you want to call it like that, just to make sure that really you can match the data and make something which is useful. So that's where I see the interest in the machine learning part, not to try and go away or ignore all of the knowledge that we have in the process, but really to respect that and make the best use of all of that knowledge that we have to try and make something that's useful.
Yeah, maybe I step in there, and I think this is also, I would have thrown this issue also at you in terms of if you wouldn't have been raised. I think with the machine learning thing, we are now having an emerging new technology that, like it was in the past with the Monte Carlo process describing the structure. So, and future will tell where it moves to, and we should have an active eye on that. I had on a flight to Seoul, I had a discussion with the head of the Max Planck Institute that is working on artificial intelligence, and the provoking question was, do you still need all these kinetics? You throw everything into an AI and it will tell you. And to be honest, we did not need any movie on the way to Seoul. We had a very vital discussion about that. And the outcome was, I think, good and quite fair. Yes, for extrapolating the physics and the kinetics and all this part is needed because the model has to know where to go and in uncertain grounds. But what you addressed is we're doing hard understanding the deviations. So is it just because the coefficients are incorrect, or do we overlook a certain mechanism or whatsoever? And I think it will be interesting to run that in parallel and see where the benefits are. So having an eye on that and see where it goes to. When moving into the process safety divisions, they are always very reluctant in releasing an AI to process control, at least for safety operations. But in terms of optimization and finding local and global minima, I think they are open, and that's it about getting a better feeling for complex interaction.
Thank you. Any more comments to this question? No. Okay, so you, I think, already partly answered the next question I wanted to throw at the panel, maybe being a bit direct there, but what, in your opinion, will be the modeling technique of the future? Would have been my next question. So where are we going, or what modeling techniques? So maybe Felix and Sabriye can start, because you have not contributed to this discussion yet, and then Nick and Markus want to answer, you can step in.
Yes, we certainly see the benefit of machine learning, the approach of machine learning in modeling, and indeed once in a while we are also challenged with what will be your fallback career when the AI takes over your job. It is. I would also second Nicolas in that the importance of addressing some of the more fundamental phenomena accurately and leaving the bits that are in the end too complex or still not within our knowledge or capability in modeling. So combining these two approaches, it's probably the sanest approach, because the machine learning models also will need the proper data to train on. And if you do not have the insights in what these should be, which comes in the end from first principles, you will not get to a efficient model generating process that's just led by AI. At least this is where we are now. I don't know how quickly things will progress, and 10 years later, I might be looking for a different job as a chef or a childminder, but for now, I'm optimistic we will still have a role. Yeah.
Thank you very much for this nice comment.
Yeah. Felix?
Yeah, I'm not so sure about this. Nobody knows what the future will be. I think it is a little dangerous to throw away the first principle models too fast. Because I hope you could see this in my presentation. There's still a lot you can do with this first principle models. With the new computational power, a lot of new fields are possible, like combining these things with CFD simulations and stuff like this. But I'm not sure. It will get more complicated, more expensive, because if you want to make new, more complex models and understand new things, you always need better sensor technology and more experiments to come to this point. So
yeah,
it's really complicated where the direction will go, and if some people are willing to spend all this money to get always more complicated. But I think that the hybrid approach, I hope I can call it like this, that Nicolas Ballard presented today, I think it's very interesting and fascinating, and maybe we will see much more of this in the future. So we will see.
Yeah, I would say if I step in there, so I would agree that we are on uncertain ground, but what I would underline is it will not disappear and nobody will be obsolete. So I think this is what I'm convinced of. Where the balances are, whether it is a lot of machine learning and a little first principles or the other way around, I don't know. But I think they will complement each other. And if you go back in history, go back to the 90s, where I was a child of the ODE modeling, of the process modeling, and Tubita was a child of the Monte Carlo modeling. And I was for the ODE part for the reason of speed. I would like to have quick answers. He was for the detailed kinetic mechanism on the branching and scission and so on. He'd say, I don't care about speed, I care about scientific truth. That was a discussion in the year 2000. In 2018, when we are honoring Harman Ray, we were both making hybrids. And we were remembering this discussion and laughing about that. I think his comment, yeah, we were young. Because it is the time is telling that we both moved into the direction of best efforts and best outcome. And then I will leave for a moment the field, but it was a very interesting conversation on the Heisen when filling a Heisenberg fellowship with machine learning and artificial intelligence in architecture. And the question of the board was, how do you, as a machine learning person, take us away the fear to be obsolete when the AI comes up? And his answer was, this will not happen because the rigorous, it was about energy efficiency of buildings. But the computation of the full computation of the energy efficiency of a building is too slow to have it as an online advisor in the design process. I'm sitting in front of a computer and I would like to have this design element, and the computer should tell me this is a bad idea, you're paying too much money to heating. And for this, the rigorous approach is too slow, and the machine or the artificial intelligence is fast enough to do that. And at the end of the day, you will do the basic evaluation anyway when you have the time, but during the design process, AI helps you to get faster. And I think it's maybe we are going a little bit in this direction. So we are learning about, quicker learning about complex interactions, which we would otherwise not do, but still we keep the rigorous process for the absolute calculation of the numbers. And I found this conversation gave quite some insight, and maybe Nick can comment that from the AI side. So this would have been one ball I would have thrown in your acre anyway.
Yeah, no, I think basically the AI and all of this machine learning stuff should just be seen as another tool, and like I think Professor Busch demonstrated in his talk, you know, historically when a new tool comes in, you find a use for it, and for what is useful is good, and for what is not useful, you use the other tools in the toolbox, and I think it will just be like that. In 20 years' time, we'll realize what it's useful for, and we'll realize that it's not useful for everything, but perhaps he's played a role in some things, and I think that pretty much sums it up. No, I don't think that we'll be out of a job for sure. And
sure.
Yeah.
Okay. Oh, thank you very much for this really nice discussion in the end. I think it indeed highlighted that, yeah, we are at an interesting point in polymer reaction engineering, looking at the modeling world and it will be interesting to see where it goes, which nice picture that you used, Nick, which tool will be used successfully. And with this, I would like to thank EFCE for organizing, especially Martin Fuchs, for organizing this nice Spotlight Talk series again. And I would very much like to thank our speakers of today's Spotlight Talks. Thank you very much for contributing with very nice, clear presentations. It was an extremely broad and nice overview of possible and successful applications of models in PRE, and also for the panel discussion in the end. And thanks for the participants for their interest. And yeah, hope to see you in the future for the next event.
Yeah, Kristina, thank you to many thanks to you and Martin for having us and organizing this. And I'm looking forward to see how these fields will evolve.
For sure. Wayne?
You.
Right then.